here's what I'm going to do. I want to show you another property of Pascal's triangle and make that my segue into the binomial theorem. Okay? It's not going to be a proof, it'll just be a demonstration. Okay? So here we go. You remember I told you that, what was the last property I showed you? Do you remember? It was the crazy one. It was the prime numbers. First we noticed that none of these guys in here were prime. The only primes appear in this counting numbers diagonals, because symmetrical, okay? And then we noticed in those prime rows, there were some weird, funky patterns, okay? Guess what? It was just getting started, okay? Now, this one is a bit harder to do. With the rows, I could show you all the rows at once, and here, we've got the prime numbers are 2, 3, 5, 7, 11. Those are the ones that are on here, right? But for this one, I'm not going to need to go all over the triangle, so I can only do it for one number at a time, but hopefully it'll be enough to show you, okay? Now, here's where we're going to begin. The smallest prime number. Smallest prime number? 2, right. As a row, it's not that interesting, right? Like, you know how we say, oh, look, all factors of 5, all factors of 7, all factors of 11, okay? But there are factors of 2 that are not in this row, right? Help me find them, okay? Are there any here? No. Okay, are there any here? Yes, okay. There's 3 of them, in fact. Cool, okay. Next row, where are the factors? The middle 2. You'd expect, okay. How about this one? Where are the factors? You've got this guy, it alternates, doesn't it? Okay. Now, so far you're like, is there something here? Well, it's symmetrical, but of course it's symmetrical, because the triangle is symmetrical. But let's just wait and see what happens, okay? Are there more numbers that are even? Not here, because they're all factors of 7, right, and nothing else. Even numbers here. There are, actually all of them except for the ones, right? How about here? Where are the factors? All except the 9s, right? Am I missing any on the next line? Let's see. Well, 10 is. 10's one, right? Cool. He's hanging out there on his own. Of course, because every second one. Yeah. How about in the middle? Well, you skip the 45. You get these guys. And the 10. Yep. Next. Are there any even numbers?
Yes.
There are. There sure are. From here.
Oh, makes a triangle.
Now, I wonder, I mean, I've run out of space on the board. But I wonder where you see this going. This shape, it has a name. This shape, it has a name. It kind of looks like this. Hold on. Hold on, there's more. Okay, there we go. Now, I could be standing here a long time. In fact, I could be standing here for infinite time, and I could never finish because this shape actually has a couple of names. I'm not done, but the broad category of shape is this is called a fractal. Right? It is self-similar. As you zoom in, for instance, see this part here. Just look at that. See that? It's like a mini version of the whole thing. Right? Can you see those 4 triangles in this one here? They're here, and here, and here, and here. You see it? Okay. And I can keep going in if I kept drawing, or if I could keep drawing. Right? You see them in the numbers. The further it goes, this triangle completes. Look, you've got these guys here, which kind of stand for these little triangles. Right? But then you've got these triangles, and I'll get more if I could draw more. Okay? Now, generally it's called a fractal. This particular fractal, because it's got triangles in it, was discovered by this guy, Sierpinski. So you've got Pascal's triangle, and within it is Sierpinski's triangle. Okay? Now, why did I show you that? I showed you that hopefully to convince you, if you weren't convinced already, there is some crazy black magic stuff happening in this triangle. Okay? There are weird patterns. We're just scratching the surface.